Alright, hi everybody. This is going to be section 2 about the structure of the atom. And we're going to go through a couple of different things. The different pieces of an atom being the protons and neutrons and the electrons. Excuse me. And how they were discovered, as well as where they're located. Alright, hi everybody. In this video, we're going to start talking about section 2 of chapter 3, where we talk about the structure of the atom. And we're going to start by just kind of giving it a definition, and then we're going to define different regions of the specific atom. So the first region is going to be the nucleus, where in the center of our atoms, we have protons and neutrons that are typically going to be joined together. And this is where I remind you that protons are positively charged and that neutrons are neutrally charged, hence the term NEU as a part of that word. From there, we're going to talk a little bit about the region outside, which is going to be electrons. All of those three different subatomic particles, protons, neutrons, and electrons, all come together, and we refer to those generically as subatomic particles. And just to kind of remind you of a couple of different facts about those subatomic particles, electrons tend to be a negative charge of 1, protons tend to be a positive charge of 1, and neutrons tend to be a 0 charge. That being said, when it comes to the mass of these different subatomic particles, protons and neutrons are going to weigh about the same, but electrons are pretty small comparatively. And one of the things I want you to recognize is, even though this guy is much more massive than this guy as far as the mass is concerned, the charges are equal and opposite of each other. So a proton has a +1 and the electron has a -1. From there, we want to talk about the different experiments that were involved in actually discovering these different subatomic particles. And the first is going to be the discovery of the electron. There are actually a couple of different experiments that helped us identify an electron's existence. The first is going to be the cathode ray, done in late 1800s by I'm trying to remember. I think this was J.J. Thomson. And what he did is he actually sent cathode rays that are going to be negatively charged through a tube, and in that cathode ray, the particles that he actually sent were then officially named electrons, and there was like a positive part of it and all of that. J.J. Thomson's experiment actually only measured the charge to mass ratio of the electron. In order to identify everything we needed to know about the electron, something else had to be done. And that was Robert Millikan's oil drop. And the oil drop experiment actually just measured the charge. So if we know the charge to mass ratio, and then we know the charge, we can actually figure out what the mass is of an electron by doing some manipulating of the math. In those particular experiments, once we joined them together, like we said, we got that mass out of it. This is going to be a picture of our cathode ray tube. So again, negatively charged particles put into the tube. There's a positively charged end and a negatively charged end. This is very similar to how like a battery would produce a current in a circuit of any kind, in that there's always a positive end and a negative end, and the negatively charged electrons moved through the tube because they are negatively charged in negative things like positive charges. The atomic nucleus was a little bit more of a cool experiment, in my opinion. It's the coolest experiment that was ever kind of produced or presented in the 1900s. And this is early 1900s with a gentleman by the name of Ernest Rutherford, who also then, of course, had some other fellow scientists that did this experiment. But we call it Rutherford's gold foil experiment for a reason. He posited that if he sent a very densely packed bundle of matter, just like a shot of particles with a positive with any electric charge towards the center of the mass of an atom, he could prove either that an atom had a positively charged nucleus, or that the atom looks like the plum pudding model, which is something that you already researched. So the plum pudding model, which you all did some research on today, had the factors of no real organization to the atom. It said, according to that model, all of the particles were just kind of randomly dispersed. And it's all based on this dessert called a plum pudding from the early 1900s that had all kinds of different random stuff in it, just kind of randomly mixed throughout. Kind of like if you think about Jell-O with fruit in it, it's just kind of randomly collected. Well, Rutherford decided that he was going to prove one way or the other how the atom's nucleus existed or not. And so by the time he came around, there wasn't really any proof that a nucleus existed. What he tried to prove was that the nucleus was real by sending a packet of energy at a piece of foil that was made of gold. And what he figured would happen is if it was a plum pudding model, he would see the light scatter in all different directions. Well, what he actually saw was that most of the particles went straight through and ended up on the other side of the gold foil and did not interact with anything in between. What he also then observed were a few bounces off of something. And what he posited was that since there were these small deflections or really wide deflections, the particles that were actually being shot towards the nucleus were being reflected or deflected, if you will, off of that positive nucleus and onto other areas. But like I said, most of his particle beams went straight through and did not interact with anything. It was the very few that actually did not that helped him prove that a densely packed nucleus was positively charged. If it was negatively charged or neutrally charged, these particles would not have behaved the same way. From there, we want to talk about how these things are actually presented. So all atomic nuclei, of course, now that we know what we know, all atomic nuclei have protons and neutrons in them. The proton, of course, still has the positive charge that's equal and opposite of the negative charge of an electron, even though the electron is so much smaller. Most atoms are going to be what we call electrically neutral, so no charge, because the number of protons are going to equal the number of electrons. The exception to that is going to be when we talk about ions in the future. And then, of course, a neutron is electrically neutral, so the neutron does not have to equal either the protons or the electrons. That being said, one of the things that we can look at is how the number of protons identifies atoms. So on the periodic table, and we'll look at this a lot closer in our next section, on the periodic table, we see a couple of different numbers associated with every single atom. Well, one of those numbers, especially the one in my classroom, is blue. That blue number is a whole number, and that's exactly the number of protons that that particular atom will always contain, and all atoms of that type will always contain the same number of of protons. So for instance, a hydrogen atom always has one proton. It's the first one on the periodic table. All atoms of hydrogen would have one proton. So the number of protons then determines our atom's identity. And understanding how the forces in the nucleus work is a kind of more high-level concept. In theory, you can understand that a proton and a neutron are going to be in there, but what keeps the protons from kind of dispelling or repelling other protons? And the answer is this idea of a nuclear force. So inside of our nucleus, there are 3 different forces that are holding particles together. One is going to be the proton-neutron force, one is going to be a proton-proton force, and one is going to be a neutron-neutron force. These are attractions between neutrons and protons that are extremely close together. When this happens, we call them nuclear forces. So it's just a really interesting type of way of describing how atoms stick together as far as their nuclei are considered. From there, we want to talk about a new unit, and that is the picometer. Since our atoms are so small, we obviously can't see them with our own eyes. We can't even really see them with a regular microscope. We need a special electron microscope to see a single atom. From there, what we want to talk about is how can we actually describe how large an atom is, and for that we need a special unit, and that's referred to as the picometer. Very, very, very small value. And when we talk about the picometer, we won't really be doing a lot of conversions or anything like that with this, but just understand that the picometer is 3 more orders of magnitude smaller than the nanometer. So if a nanometer is 1 × 10⁹ nanometers in 1 meter, the picometer is 1 × 10⁻12 picometers in 1 meter. Okay, so it's a very, very, very small number, 1 × 10⁻12 meters, if you will. All right, that concludes section 2. So I am going to post section 3 tomorrow just so that you have it, but your homework for tonight was just to watch sections 1 and 2 of our lecture. Have a good one.